first of all, let me thank the organizers of this workshop for this invitation, and also people from IPAM for their continuous effort in maintaining the high level of this workshop, even in this new online fashion that I don't like actually, but thanks a lot for being so effective in this organization. So I will deal with the platoon control in freeway traffic networks. Let me first of all mention the people with whom I've been working in these last years on this topic. So Silvia, Cecilia, Enrico, who still works here in Genova, Claudia, who moved to the Polytechnic of Turin, and Professor Antonella Ferrara from the University of Pavia, with whom we have a continuous and very fruitful collaboration a long time. Also, I've put a picture of the university campus where we work because I like it a lot. And so anytime I'm proud of that, and I put a photo of that. I will take just some slides to, let's say, frame the research activity that we did in these last years, just to better focus on what we were involved on, and also to better present the way in which we face the platoon control, that is the main topic of this presentation. So first of all, we have been working a lot about freeway networks. So we are dealing with road transportation and freeways. And the main objective of our research activity has been for long the possibility of improving sustainability. So we would like to tackle traffic control in a sustainable vision, in a sense that we do not only want to reduce congestion, which is a typical objective function in working with freeway traffic, but we also want to take care of some other performance indicators, objective functions that are just related to a safe and sustainable mobility. So we have worked a lot defining and using some performance indicators as pollutant emissions, noise reduction, environmental impact, as well as safety. Always together with the minimization of congestion phenomena, of course. The main ingredients in this sense for a freeway traffic control scheme are here presented. Of course, I'm saying things that are very well known to the audience, but anyway, I just recover some main things. Of course, we are dealing with the freeway network, which is definitely a large-scale process with intrinsically nonlinear dynamics. So it's a nice test field for modeling and control techniques because it's a real complex process. In this field, we can identify several control actions that are typically used either on the mainstream as variable speed limitations or lane control or route guidance, or at the on-ramp, like the well-known ramp metering approach, which is very widespread, and I've seen a lot of work by the scientific community in the last decades. Dealing with the control objectives that we can define, of course, something related to congestion, so the possibility of minimizing the total time spent by drivers in the system, together with, in our vision, the total emissions for pollutant in the system, or the total expected number of crashes in the system, again, to deal with safety, or some other control objectives, as instance, as I told, related to fuel consumption or noise reduction. Again, in a sense that we would like to improve the overall sustainability of mobility on freeway networks. Further on, of course, what do we need to face this problem? We need suitable models, and we do not only need the traffic flow models, but also emission models and relations that let us associate several sustainability indexes with the traffic conditions, as we did as instance for safety. We succeeded in associated the expected number of crashes in a system, in a freeway system, with the traffic densities, and several other models that, of course, can be useful in this sense. Further on, we have to define the structure of the control scheme that we want to adopt. Typically, we have two extreme cases: local control, in which, of course, dealing with feedback control, we define a control algorithm, a control action based on a local measurement, just local measurements, or at the opposite, a coordinated control in which we assume to have a traffic controller knowing all the state measurements of the system of the network and designing the control action depending on state measurements on the whole system. Finally, we may use different control methodologies, starting from very simple feedback control laws and going on with the optimal control, model predictive control, decentralized control, and so on and so forth, as we can easily find in the very wide literature that is available for freeway traffic control. We tried several things in this field. So we tried several modeling approaches, several control schemes, and several control methodologies. I've just listed some here, but I do not want to make a list of references, neither ours nor of the existing researchers, because they are a very long list, actually. I just put some points, and of course, I'm more than happy to share if somebody is interested. Just putting the attention on some keywords that we are interested in. Event-triggered control, we tried to solve the control problem by defining some event-triggered logic, in a sense that we do not keep the control action unvaried, but we change it depending on the occurrence of some specific events in the system. We adopted both a centralized and decentralized scheme, so approximately equivalent to what I've just mentioned as coordinated or local control, not exactly in that way, but anyway, with this in mind. We worked a lot with model predictive control. Model predictive control, of course, is a very powerful technique for solving optimal control problems in applicative fields. I was looking back at the literature now, and I found some very, very early approach that we tried to work on approximately 20 years ago. I've reported those here, not exactly because they are so interesting, but because it has been curious for me to note that 20 years ago, we tackled the model predictive control scheme by trying to approximate the control function with some functional approximators that were related to neural networks. It was very interesting. It promised to be very effective, but we then gave up, we abandoned that approach because actually we lacked data. So we had no enough data to train the neural networks effectively and to use them as functional approximators. It would be really very nice to make a comparison now with the existing reinforcement learning approaches that I see that instead now have lots of data, and so they can count on a very wide information. They still use neural networks in many cases, so it would be nice to see a comparison between those very old approaches and the new ones. I believe these are much more powerful. But anyway, the method is, seems to be very similar, and it would be nice to couple the two things. Also because I believe that reinforcement learning approaches, machine learning approaches could gain a lot by including the knowledge about the system dynamics. So coupling these approaches with the knowledge that we have about the process dynamics could be very powerful. And then we also did some feedback control, simple rules, simple feedback approaches that show to be actually less effective than coordinated control, but really powerful from an applicative point of view. So we also tried to go and define some feedback control approach. Okay, this is something that is reported in some works that we did, and this is just the background to understand how we did started working about platoon control. We tried to exploit some lessons that we learned. So what did we learn? First point, this is very interesting in my opinion. As I told, we worked a lot about sustainability issues, about sustainability indexes. It is very clear actually after some time that congestion reduction and the optimization of the majority of sustainability-related cost functions are equivalent problems. So if you keep a low congestion in your network, you also improve all those sustainability-related objectives. So it's worth going on with considering the way in which we can manage and prevent congestion, because this goes in the same direction as having a safer and more sustainable mobility on the system. The main point that can be identified in this sense is that the main conflicting issue in networks in freeway networks actually refers to what happens in the mainstream and what happens at the on-ramps. This is the only conflicting issue, and this is the only thing that makes the difference when you take care of different control functions. As instance, if you want to minimize pollutant emissions for trucks, it's worth making them enter the freeway instead of remaining at the on-ramps, because there they have a higher pollutant emissions. And this is a case in which RAM metering actually is different if you only take care of a congestion or you also take care of emissions. So only in this sense, it's worth differentiating approaches dealing with the sustainability. Otherwise, tackling congestion also goes in the direction of having a sustainable system. The other point, which is important in my opinion, is the fact that definitely coordinated control schemes may also including prediction capabilities as model predictive controls as instance are very effective actually, but still their practical applicability must improve. Still, there are some computational issues and also some aspects related to the communication effort that you need that are on the ground. And it's really difficult to apply these schemes in applicative case studies, on real case studies, due to this point. It's difficult to convince the freeway managers to adopt a method like this if you're not sure that it will run in few minutes, even less than 1 minute. And so this point is very important to be considered in defining control approaches for large-scale processes as freeway networks are. Third point that we have in mind is the fact that anytime you have to calibrate, to validate your system on real data. And this is an important point. This is something that actually in the past we have a little bit neglected at the price of defining approaches that then may not be suitable for any kind of test field. Many times this is due to the fact that data are not so available actually. I don't know in the US, but in Europe it's not so common to have a good amount of data related to a test field. There are not so many sensors there, and so up to now, this point is critical if you want to see a real calibration of the model or the control technique that you are using. Of course, we do now, we can use now new sources of data. Vehicles will be sources of data, and also a lot of different methods can be used, just exploiting the connections, that is the connectivity of vehicles. And so we do hope to see the amount of data increase in the next time. Okay, with this in mind, how did we face platoon control? That is the topic of this presentation. Of course, now we have to change the paradigm. We have to move from road-based control schemes, as the ones that we treated up to now, to vehicle-based control ones. So we have to put our attention on the way in which vehicle, and especially automated and connected vehicles, can be included in a freeway traffic control scheme in which they can be both sensors and actuators. So they can actuate control actions, specifically, I believe, speed limitations, but they also can be sensors, so they can be sources for information for the whole control scheme. Okay, I was mentioning, how did we face this problem? In this time, we decided to start in a different way with respect to the past, and so we decided to start with very simple control schemes. We have to understand a little bit the features, the main features, the main characteristics of the process that we have to consider. So we started with very simple approaches. We imagined to have a network, of course, as usual, represented by links, origin links, and nodes. And in this network, we suppose to have a certain number of platoons of tracks that move along the network. We now imagine that these platoons have already been decided, so we know their paths and we know the time in which they would like to enter the network. We do not decide about this. And also we do not decide about the control action that is necessary to keep platoon moving together. We just would like to understand whether platoons can be used to improve the traffic conditions by exploiting their speed as a speed limitation. And this is what we are trying to do in this approach. So the control action that we are considering here is just the speed of each platoon. This speed is determined, is our control variable, of course, and it is determined, as I said, in a very simple control law, which is a PI type feedback control law, in which we use a discretized version of the controller, and we use measurements about the traffic density that are necessary to define the control error inside the feedback control law. This approach is very simple. It's a very well-known control structure. We have introduced some features in this control law. And specifically, the first one is that when we define the measurement that we need to design, to use the control error, this measurement is not just one local measurement downstream the section in which we are, but it is computed as an average density. So we try to extend a little bit the information that is used inside the local controller, not using just one density in one specific location, but averaging the densities that are downstream the location in which the platoon is. This could be a starting point for making the controller a little bit aware of traffic conditions along the road. The reference point for the density, as it is usually done, is the critical density, but this can be chosen also in a different way. And also the feedback control law includes two gain parameters, and the way in which these are defined, of course, is a matter of work. Further on, the speed of platoons has to be bounded, of course. We have defined the bounds in this way. First of all, we imagine that each platoon has a minimum speed, which is allowed for that platoon. And instead, the maximum value of the speed is defined depending on a desired value of the platoon, of the speed of the platoon, and the speed, the traffic mean speed in the section where the platoon is located. So this is the control law. It is very simple, of course, nothing, we do not want to show, to prove any kind of theoretical properties. We would just like to use it and see whether it is effective or not. This is not easy, of course, because to use the control action, we have to adopt a certain model or a certain simulation model or a prediction model to understand which is the effectiveness of this control law. we tried two directions in this sense. The first one, it goes through the definition of a new model, which incorporates the presence of platoons inside a macroscopic framework. So this is what we have called the micro-macro model. It is because the model includes two levels. The first one is a classical destination-oriented network model. It is a macroscopic model, the well-known METANET model, which is not that good for proving theoretical properties, but it shows good prediction capabilities. So we chose it for this reason. And inside this macroscopic model, we want to include a microscopic level, just dealing with the movements of platoons, and so taking care of their presence inside the network, their position, and their speed. Okay, the objective would be that of understanding the interactions also between these two modeling levels. I won't go into details about the macroscopic level. It is METANET. It is very well known. We very well know its advantages and also its limitations. But anyway, it is based on state equations that take care of the dynamics of the traffic speeds, traffic densities, and traffic mean speeds. Also, we used in the model the specific dynamic equations for the queue length on the on-ramps. In case we want to use ramp metering in some sense, this is useful to include. And also the METANET model embeds a certain set of flow balance equations in nodes, of course, doing a correct balance of destination-oriented traffic volumes in node. Anyway, the model is very well established, and so I won't go into details about it. What about the microscopic level? Okay, we have assumed that each platoon has a given side and an assigned path. We won't decide about that. We define instead the state equation for the distance covered by the platoon. This is the cumulative distance covered by the platoon from its appearance in the network. And the speed of the platoon is defined with the minimum that we have already discussed some slides ago. Okay, further on, the microscopic level also takes care of the possibility that platoons have to enter the network. So we have tried to take care of the fact that in highly congested situations, it could happen that platoons do not succeed even in entering the network. And so we have defined some conditions to also analyze this case that have been defined in this way. Again, I do not want to give too much details. These are very simple relations, actually. And we have also included a dynamic evolution of buffers for platoons, just to take care of the possibility that platoons have to wait on the on-ramp links before entering the freeway. With all these relations, of course, we have defined the two modeling levels. Still, we have to model some interactions. We've done this by considering not only the, let's say, two different kinds of traffic densities inside each section, the one which is related to normal vehicles, and the one which is related to the occupancy of platoons, of course, in case they are present in the section. This new traffic density is used, of course, to anytime model the real occupancy of each section, but also it is used as the argument of the mean of the dynamic equations related to the traffic mean speeds. And so anytime we have to include the traffic density inside the speed equations, we use this global traffic density, then also including the possible presence of platoons. Of course, this means that we are including here some interaction of platoons with the normal traffic flow, in a sense that this density, of course, influences the speeds of the whole traffic flow. In this dynamic equation of mean speeds, of course, we have the presence of the traffic fundamental diagram here. In this model, we used a very classical form of the traffic fundamental diagram. We are working on this. Of course, we believe that we have to find different forms, different structures for the steady state speed density relationship. These structures should consider two different aspects, in my opinion. One is the fact that we are dealing with mixed traffic. This is one point. We have to understand how the presence of automatic vehicles and platoons, in this case, specifically influence the steady state relationship of normal traffic. But also in this case, in this specific case in which we want to do a speed control, we have to take care to the fact that the traffic fundamental diagram for systems in which speed limitations are adopted is not exactly really standardized. So there are several forms for the traffic fundamental diagrams, or better, the steady state speed density relationships with the speed limitations. But I believe we do not have yet a complete and well-recognized form for this relationship. We are working on this. I just listed here some works that deal with the definition of the fundamental diagram with the presence of mixed traffic flow and also with variable speed limitations. Of course, this list is not exhaustive at all. I just reported some works that we are considering. Again, dealing with either the presence of connected vehicles or the fact that we are using speed limitations. These are the two aspects that are needed. Okay, just some results of this very, very preliminary work. So we consider a freeway with 6 links that have a certain section. Of course, we are working in simulation. We have several on-ramps here. We have a time horizon of 2.5 hours. And we imagine to have 3 platoons, each with an occupancy of equal to 10 vehicles inside the freeway, also with the desired speed of 85 kilometers per hour. We did some simulation here, and of course we used the micro-macro model for testing the effectiveness of the control action. What did we derive now? Okay, to have an evaluation, a quantitative evaluation of the effectiveness of the control, not only for normal traffic, but also for the platoons, we defined 2 indexes. The first one computes the time spent in the congested area by each platoon. It is, of course, the sum of the time interval during which the platoon is in a section which is congested. And the second index instead is related to the smoothness of the speed profile of the platoon. We very well know that trucks would like and also need to move with smooth speed profiles. And so we also wanted to compute this index in order to take care of this aspect. Okay, we did some simulation in this case. So here is the no control case. In these 2 diagrams, we can find the traffic density and the traffic mean speeds along the network in the long time. The colors, of course, are red when something wrong is happening. So if the traffic density is very high and the traffic speed is very low. And so we can see clearly that there is a severe congestion in this system. Coming to some zoom into what the control is doing. In this diagram, we show the traffic density in section M3, which is the most congested along this small freeway stretch, and along time. The blue line is the traffic density evolution without control. So it is clear that it hits the maximum value of the traffic density, remain there for long. And so the no control case is highly congested. The red line and grid lines instead are the traffic densities obtained by using our control technique. The red lines is referred to a case in which we just use it with standard gain parameters, so without optimizing the controller parameters. You see that, of course, the 3 platoons are not able to completely prevent or reduce congestion. They are doing something good, but of course, congestion is still there in both cases. Of course, optimizing the gain parameters of the controller lets us obtain a better result, of course, in this case. Of course, we have to investigate a lot at this point, but anyway, it seems worth having some effort in deriving optimized values of the parameters. This is, sorry, I go back. This is what can be analyzed. Of course, we can do also much more than this. Anyway, this is referred to what happens for normal traffic. So normal traffic is interested in reduction of congestion, and something can be done with this approach. But what about platoons? We would also like to understand what happens to platoons and if we are worsening their situations. So we have reported here the profile of the platoon speed for 2 of them. Again, the blue line is without control and the red line is in the controlled case. Of course, we have seen that congestion is still there. So in both cases, the platoons have to slow down a lot and to travel along the congested sections with very low speeds. But what can be seen here is that with the control approach, it happens that you see that there's a smoother decrease in the profile speed of each platoon up to a certain point. So they are a little bit, their profile speed is starts decreasing early with respect to the case without control, and this is something good for platoons. Then they have the congestion has been a little bit reduced, so they travel with the minimum speed for a shorter time period, and then they go back to the normal conditions, of course, in the same way as they would have done without control. This happens in a very similar way for all the platoons. Anyway, we computed those indexes that we mentioned before, and we can see that the presence of platoons in congested areas is reduced, not so much, but it is anyway reduced, together with also, and it is also reduced that index that counted for abrupt variations of the speeds of the platoons. This was clear also for in the pictures. These are slight variations actually, but still it's promising to try to also improve this control scheme. This is what we try to do, what we are working on now. We are working about the possibility of calibrating the model through AIMSON, to a microscopic simulation tool. Actually, this is the second way in which we can test the control action, doing simulation with AIMSON. We are working on that, but we are not completely we have not yet succeeded in suitably modeling platoons inside AIMSON. We have not completely understood how this can be done in an effective way. We have some application programming interface. We are trying to do something, but we have not yet reached a good result. As I told, we are analyzing the fundamental diagram in such a way that we can use a more affordable version of it, or even more realistic. And also we have tried to design more sophisticated control architectures. This one was really very simple. To do this, I present very preliminary results on which we are working right now. We tried to use a control architecture that we have already defined for general multi-class traffic networks.
5 minutes, okay, thanks.
Yes, thanks. in this control architecture is anyway based on local controller. So we are not going in the direction of defining complex control problems. We will try, of course, but up to now, still we are dealing with local controllers of the same type as before, so PI type feedback regulators, but we wanted to include them in a certain hierarchical architecture in which we have a more sophisticated approach in which the control parameters, the control law parameters are defined not only in a local algorithm, but with something more, with some more information. This architecture has been defined both in a centralized version and in a decentralized one. In the centralized approach, we imagine to have a supervisor here, which knows all the system state, and being equipped with some predicting capabilities, decides whether it is necessary to change the control law parameters, and it may also decide whether it is worth controlling a certain portion of the network or not. Then we again have a low level made up of local controllers. Again, they use measurements not only in one point, in one location, but along a certain number of sections that we have called the cluster. And it is important to say that the event-triggered supervisor in our idea could be used also to define the dimension, the size of these clusters, even dynamically with respect to the traffic conditions. The low level, of course, is made up of local controllers, as the ones that we have already said. And this is what refers to the centralized version of this scheme. We also have in mind to use a decentralized scheme in which we do not make use of the supervisor. We only have local control algorithms, but again, these are equipped with some predicting capabilities. And so they do not only measure along the cluster, but they also do some reasoning about what is going to happen to this cluster in the near future. We have done some very preliminary tests with these two schemes. Here I have recovered exactly the case that I've described previously. So we have exactly the same network. We have the blue line, which again is the no control case. The green line is what we got with just with the simple feedback regulator. And instead, the red line is what we have got up to now with the decentralized scheme, whereas the yellow line refers to the centralized approach. They are all very similar, you see, as it could be guessed, the centralized approach seems to be the best. Still, we do not completely afford on these results. We see some oscillations up and there, maybe because this, I forgot to say that this supervisor is equipped with an event-triggered logic. So the way in which it decides whether it is worth changing the control parameters is based on an event-triggered logic, and so on the verification of some specific thresholds of the system state. So maybe that this event-triggered logic has to be refined a little bit, has to be investigated more, because we see some specific points in which something strange happens. Anyway, it seems promising to go in this direction and see whether these control architectures can be useful for platoon control along freeways. I can come to conclusions. I hope to be on time. I believe that the introduction of automated and connected vehicles, as everybody of us knows, is a very, very nice opportunity to revise the control schemes that we have worked on up to now. A lot of attention is devoted now to two main aspects. The first one is that of evaluating the system performance in mixed traffic. So still we have to quantify what happens in the system in these newly designed conditions. And also now we have the possibility of defining new modeling and control methods and schemes on a vehicle-based control framework. So I believe we are now in a moment in which we have lots of opportunities. Still, we have to remember what we have learned in the past. But anyway, we can move to a smarter and safer mobility, I believe, also exploiting this mobility revolution devoted to automated and connected vehicles.
Great.
That's all from my side. Thank you.